Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we explore section 1.4 in the Big Ideas Math Integrated Math 1 textbook on solving absolute value equations. You're going to see the symbols, they look like this. There's basically tall vertical brackets, bigger than a lowercase l, if you will, or a capital I. Absolute values you might have heard before as ways to turn something positive. Sort of. We're going to talk more about its true definition. I'm sure the book's going to do that. We're going to start with the lecture portion, and then we're going to go into the problem set. Now, everything we did from 1.1 to 1.3 applies in solving equations. Just another added step to them. Absolute values are their own detour from the thing. Like, it's not like we're going to build off absolute values and do the next thing per se, but this is just a detour from what we're taking here, and then we're going to do another detour from that eventually to do section 1.5 to conclude the chapter. So guys, without further ado, I'm going to go ahead and get started. If you jump to the description section down below, you can download this PDF, and you can also follow along, find the timestamps to either the problem set or the lecture portion, which I'm going to start right now. The playlist is also linked down below. Without further ado, I'm going to go ahead and get started. We're going to solve absolute value equations. They're these guys right here. We're going to solve equations involving two absolute values, like another one of these. We're going to identify special solutions of absolute value equations. Remember when we talked about no solutions and things like that before? Yeah, some things might apply here as well. We got to come up with what they are. Solving absolute value equations. An absolute value equation is an equation that contains an absolute value expression. So it seems like they've defined what absolute values, oh yeah, absolute values were a previous term before. So absolute value, guys, means distance from zero. That's its true definition. So when we talk about distance from zero, we're talking about how far something is from zero. If you consider a number line, and here's zero on it, here's 1, 2, 3, and -1, -2, -3, right? How far away is 3 from zero? It's 3 away. How far away is -3 from zero? It's 3 away. It's regardless of direction, that's how far away it is. That's why some people say turn it positive. But you have to be careful when you use the turn it positive phrasing. Not all minuses just turn into pluses, nothing like that. No, we'll talk more about it. Anyway, it's an equation that contains an absolute value expression. Now, if it contains the expression, it's likely your variable, like x, would be inside of that expression. You can solve these types of equations by solving two related linear quantities. Now, here are a couple of properties of absolute values that we want to understand. The first one is the one we were talking about. The absolute value of a is greater than or equal to 0. That means if you have a number inside of there, we're asking how far away is a number from 0 regardless of direction. The smallest a number can be away from 0 distance-wise is 0. And from there, it's only positive results out from that. So that's the first thing. So as you see that, when you take the absolute value of a negative number, it becomes the absolute, it's equal to the absolute value of that number. Meaning whether you switch the sign or not, they will be equal to each other. The absolute value of a product is equal to the product of two absolute values. If you have a need to split one absolute value into two for any particular reason, we can do so. We'll talk about that when it comes up with it. And same with a quotient as well. We can split it up into two things here, provided you're never dividing by 0, which, we're not tricking ourselves into that. It's just not going to happen. Okay, solving absolute value equations. To solve an absolute value equation, this means now what you see here is the function itself, the absolute value. It's on its own side of the equation, and it's equal to some constant value c when c is greater than or equal to 0. You can solve the related linear equations either ax plus b equals c or ax plus b equals -c. Now, this is one of those kind of mathy things that's a little like, what are they talking about? What they're saying is you can be taking the absolute value of something, right? Our goal is to solve for x, but we have to do some things along the way. We're not talking about solving for x just yet. We're talking about what we can take the absolute value of to get this other number. Now, we can't take the absolute value of a number and get a negative out. That's why they're saying c has to be 0 or positive. If it's not, there's no solution, and we'll get to those. But if it's 0 or positive, let's talk positive. If it's positive, one of two things can apply. When I take the absolute value of this number and I get c, this thing could either have been positive c or negative c inside of here. Okay? Now, we're going to see some examples, and I want to make sure to point to those, but those are the two conditions that we set up in order to solve this. There will be, potentially, more than one answer for x. Because there's possibly a value for x that when you plug it into here and compute the things, remember a and b would be other numbers. When you plug it into there, maybe it becomes 3, and the absolute value of 3 is 3. Or you plug in a certain value of x, compute it all, and it becomes -3, and the absolute value of -3 is also 3. So there's possibly more than one answer in these. Let's take a look at some examples here. Solving each equation, graph the solutions if possible. When they say graph, they mean on a number line, just plotting the points there. They say absolute value of x minus 4 equals 6. This absolute value is by itself, by the way. That's something we're going to be kind of looking to do. Obviously, they're starting off that way. But because it's by itself, ask yourself, what two numbers can I take the absolute value of to get 6? Don't worry about x. Don't worry about x. We're worrying about x minus 4. What can I take the absolute value of to get 6? I can take the absolute value of 6 to get 6, and I can take the absolute value of negative 6 to get 6. We're saying that x minus 4, this inside guy, can either be 6 or negative 6, and in which case we can solve for x in either situation. Because it's x minus 4 equals 6, we get to add 4 to both sides. And by the way, here on out, I'm probably not going to color code my actions in between, at least not separately. I'll just kind of write it. Add 4 to both sides and we get x equals 10 or x equals negative 2. Now, those are two different answers. It's not like it's just positive, negative version of the same value. So I said plot on a number line. Now, why are they doing this, 10 and negative 2, plotting them like that? To remind you that these two both are 6 units away from 4. Why does it matter to be 6 units away from 4? Because our number minus 4 equals 6 or negative 6. That's our distance from there. So 6 units away from there. Now the next one is 3x, absolute value of 3x plus 1 equals negative 5. What can I take the absolute value of to get negative 5? Don't say 5 and negative 5. Remember, absolute value of a number turns positive, distance from 0. You can't do this. The absolute value of an expression must be greater than or equal to 0. The expression absolute value of 3x plus 1 cannot equal negative 5. The equation has no solution. Okay. Let's go to the next set of problems. Now, I mentioned that we want to get the absolute value function by itself. In this particular example here, it's not yet by itself. The thing I have to take the absolute value of is not going to be the negative 4 or whatever right here, not until I have this thing alone. Why isn't it alone? 10 is subtracting from it. So what do we got to do? Add 10 to both sides. This actually reveals the true number we're taking the absolute value of to get. It's not negative 4, it's 6. So the absolute value of 3x plus 9 equals 6. Therefore, 3x plus 9 can equal 6 or negative 6. And those are the two setups that we create. You might ask, where did the absolute values go? Or, you might say, hey, just get rid of the absolute values. We're not really getting rid of the absolute values. We're more looking inside the absolute value function, right? The thing we take the absolute value of 6 could have been a 6 or negative 6. So the thing inside of here, that's where the absolute value goes. Anyway, you do some of that algebra work that we're so accustomed to doing. Subtract 9 from both sides, divide by 3. Subtract 9 from both sides, divide by 3. But we might get different answers because 6 minus 9 ain't the same as negative 6 minus 9, right? One's negative 3, one's negative 15. And we get negative 1 and negative 5. They're not asking us to graph, so we'll leave it. Writing an absolute value equation. Okay. I don't do that very often, but let's see. In a cheerleading competition, the minimum length, and cover the cheerleaders so we can see the work. The minimum length of a routine is 4 minutes. The maximum length of a routine is 5 minutes. So minimum, maximum, anywhere from 4 to 5. Write an absolute value equation that represents the minimum and maximum lengths. So what you need to do, and this is where the graph thing will make sense, is how far away are you from the middle value, right? The distance. We got min, we got max. We want to be somewhere in between there and find those values that are allowed. So in this case, here's 4, here's 5 on a number line, a lot of decimals in between, and they said find half the distance in between there. So from 4 to 5, that entire distance is 1. They're saying use a number line to find the halfway point between. Half of 1 is 0.5, 0.5 away from 4, 0.5 away from 5 is 4.5. Now 4.5 is the number that goes inside here. X minus 4.5 equals 0.5, and that's how we're going to write that thing. Okay, so we got to go that far away in either direction from there. We might even do some, you know how I might do it is I might come up with like what the value is in this case, the 0.5 part, and say this is either 0.5 or negative 0.5, and then have, no, you know what, this is fine, but you can see where they're coming up with this right here, because if I add 4.5 to both sides, technically what I'm doing, x minus 4.5 either equals 0.5 or x minus 4.5 equals negative 0.5. When you add 4.5 over, you're thinking x equals 4.5 plus 0.5 and x equals 4.5 minus 0.5. So 4.5 is the middle value that they attain where we add and subtract from it. You can see this double check that when you substitute 4 and 5 from there, that they're both half away from there. It's how far away they are from the middle. Okay. Solving equations with two absolute values. Interesting. If I take the absolute values of either side and they turn positive, either set could have been positive or negative to begin with, right? So we have to find values of x. To solve this, we solve the related linear equations. Either ax plus b, the inside, can equal the positive version of cx plus d, or it can equal the negative version of cx plus d. Now, remember, cx plus d is an entire quantity, so you don't just make the cx part negative, you make the whole thing negative, almost as if you distribute that negative into there. So that's what we're going to have to do in a scenario like this. You make two different situations in which you want to try and solve for x. Now, there's more we have to say about this in a moment. Let's check out some examples. Part A, 3x minus absolute value of 3x minus 4 equals absolute value of x. Let's treat the two conditions, that 3x minus 4 could equal positive x or negative x. Notice that we're never doing anything with the negative, the opposite of 3x minus 4, but that's because we're already switching one of the signs. And that's the point that they were making before, that the absolute value of a equals the opposite of the absolute value of a, that kind of thing. Now, in these cases here, we're solving for x. That means we got to get x's on one side of the equation. So what do? They subtract x from both sides in this scenario, then add 4 to both sides, then divide both sides by 2. They get x equals 2. Or add x to both sides, add 4 to both sides, and then divide both sides by 4. They get x equals 1. They got 2 and 1, and they're double checking them. This is actually going to be kind of an important thing for us to look at eventually. 3 times 2 minus 4 is 6, minus 4, which is 2. Absolute value of 2 is 2. And you plug in 1 to both of them. 3 times 1 minus 4 is negative 1. Absolute value of negative 1 is 1. You can see that on this side, this turns into absolute value of, and we're still good either way. Now, the second one has a 2 hanging on the outside. You've heard me kind of state before that, well, we want to get the absolute value alone. But there are two different absolute values. But here's the thing. 2 is already a positive number. You know, we're good on that front. You could take the absolute value of 2 and still be good and put it within that property. Either way, we're all good with that 2 kind of hanging out and doing its thing. As long as it's not a sum or difference, then I think we're pretty good on that. If it was, we'd run into a little bit of a mess of trouble. I'd want to think about how to talk to you about that kind of problem. But for now, we're saying that this guy either equals the positive version of this number or the negative version of this number. Now recognize the 2 is kind of hanging outside of the absolute value, but 2 times negative 1 is still negative 2 if they really wanted to do that. As you can tell, when they distribute the negative into these, then they distribute 2, so it's like negative 2 went into this anyway. And then they do some of their algebra stuff to solve. And like I said, this is stuff we've done before, so I'm kind of leaving it as it is. Get x's on one side, get constants on the other side, and divide, get an answer. Get x's on one side here, get constants on one side, divide, and get an answer. It looks like we're going to get some decimals here and there. What can you do? So negative 6 and 0.8. Looks like they did not do a double check for that problem there. Okay, let's talk about some special solutions. Now, we already saw something where we had a no solution case because we can't take the absolute value of a negative. But what if you could proceed on a problem that has an absolute value and you attempt to solve and all is looking good until when you substitute it into the equation, something doesn't work out? There are things known as extraneous solutions. An extraneous solution is an apparent solution that must be rejected because it does not satisfy the original equation. You see, keep in mind, we have this original equation right here, and we create conditions for it that alter the appearance of the equation. We got rid of the absolute value. Things might change. Things might change, especially because, and this is the only time that we're really going to be worried about this, we have a variable outside of the absolute value for which we are introspectively looking into. Because that x could have been positive or negative or whatever sign that it is that alters whatever happens on that side, completely changes what's going on. I could explain this more if we graphed absolute value functions, and I don't mean on a number line, I mean on an XY axis, but you don't do that until IM2. So I'm not going to reveal it that way. I think for now it's kind of one of those trust things. Obviously, we're going to see when it doesn't work, but as far as why it doesn't work, it would make much more sense if we talked about it in graphing form, and we're not going to be doing that. If they have some version of a number line graph thing we can talk about, great. Otherwise, we're not going to be able to do it. Anyway, so this thing either equals positive or negative 4x. Do what you got to do to solve. They decide to subtract 2x. That's fine. Divide by your numbers, and they get these answers. Now, when you try 6, it works. 2 times 6 plus 12 is 24. Absolute value of 24 is 4 times 6, which is 24. That's all good. Is that a homer? What happened? Oh, that was just a... Was that a homer? Hey, oh, look at that. Anyway, now, let's try negative 2. 2 times negative 2 is negative 4 plus 12 is 8. Absolute value of 8 is 8. The problem is this becomes 4 times negative 2, which is negative 8, and that doesn't have an absolute value there. So see, it kind of got altered. If there was an absolute value there, we'd feel pretty good about things. But without it there, it says 8 equals negative 8, and that ain't true. They don't equal each other. Therefore, negative 2 is considered an extraneous solution. So we reject it. It doesn't count. The only solution is x equals 6. So this is a case we're definitely going to have to check on these. Will it always happen? No, not necessarily. It's possible to have two solutions still. We want to check on these especially when you have a variable outside of the absolute value for which you're kind of switching signs on the other side for. That's the case we got to look into these solutions. Anything else they might ask you to check just for the sake of checking. These ones are for pure extraneous solution scenarios. Solving an equation with two absolute values. Hey, it's possible. It's possible to have some sort of things here. Let's see. By creating the expression and this opposite, right? This either equals positive or negative, x plus 11. Notice that what happens here, negative x minus 11 distributes and you solve, you get x equals negative 8. All's good. All's good. But here, when you solve this one and set for the positive one, you get a no solution thing. You get a false statement. It actually never intersects. And I want to think about what that appears as when you do that on a graph. I'm trying to think of the reason for why that would occur. I think I have some instance of it. I have some inkling of it. But you have a false statement here because you have a no solution case. So there's only one solution, which is x equals negative 8. So the only extraneous solution check that we're really, it says always check your solutions in the original, make sure they're not extraneous. The only real extraneous solution check that I'm very wary about and I really want to make sure for are these ones right here without that on the outside. It's possible that something can happen here as well. But I think over here, you're more likely to hit the no solution case beforehand on extraneity, if that's a word. All right, that's the end of the lecture portion. We're going to jump into the problem set starting with numbers 1 and 2, and then we're diving into a total of 61 problems. Well, we go up to problem number 61. So number 1 on vocabulary, what is an extraneous solution? It's a solution that we obtain throughout the equation. Woo. It is a solution that we obtain throughout our progress of the equation that does not satisfy the original equation. I was going to say condition. That does not satisfy the original equation. Reason being, again, we probably want to look more into that if you were actually graphing absolute value functions, but we're changing the nature of the equation. We turned something that was an absolute value function into a straight linear function, and transforming it can cause different things to snap, basically, to break. And that's what happens there. Will it always? No. There's absolutely chances where nothing's extraneous in those situations. You got to be aware of that. Without calculating, how do you know that the equation absolute value of 4x minus 7 equals negative 1 is no solution? Because you can't take the absolute value of a number and get a negative result. You can't take the absolute value of a number and get a negative result. You can get positive, you can get 0. You can't get negative by taking absolute value. So again, that's where people might say, make it positive. But if you've noticed, guys, we have looked at equations, even this one, 4x minus 7, absolute value of 4x minus 7. We don't turn it into 4x plus 7. That's not what we're doing. 4x minus 7 represents a number and a quantity after substituting x times 4 and minus 7. And then you take the absolute value of whatever that is. So if that number's negative, sure, it turns positive. That's how far is it from 0. 4x minus 7, not the x value. So just keep that in mind when we're doing it. Let's go ahead and get started on numbers 3 through 61. We have quite a handful to do. I have quite a lot of things to write, especially if they ask us to check solutions with graphs. So let's get started. Okay, they're going to ask us to simplify the expressions first. They're just getting your hands wet, your feet wet, I guess, not your hands. They're getting your feet wet when it comes to evaluating absolute values and what it means. Not much to say on these. The absolute value of negative 9 is 9. Negative 9 is 9 units away from 0. We're all good. Number 4, negative absolute value of 15. Notice the negative absolute value of 15, it's the opposite of the absolute value of 15. Absolute value of 15 is 15, and opposite of 15 is negative 15. So it's not positive 15 as an answer, right? You don't even need this second step right there, but I'm just giving you the idea that we're taking the opposite of whatever the absolute value of 15 is. As we lead into this one, number 5, we have absolute value of 14 minus absolute value of negative 14. So same thing. The minus on the outside has nothing to do with this portion right here other than we're subtracting it. But we're not subtracting a negative, we're subtracting the absolute value of something. Whoops, absolute value of 14 is 14. And then we're subtracting over here 14. because that's the absolute value of negative 14, which is 0. Number 6, is it the same as the last problem? Not quite. There's addition in between. Doesn't matter that these are opposite signs because we're taking their absolute values. Absolute value of negative 3 is 3. Absolute value of 3 is 3. We're adding both of them, and we get 6. I wish every question was like this. This would be a very fast thing. It could be this fast, but I have to slow down a lot of things. You know that. Number 7. Opposite of the absolute value of negative 5 times negative 7. Now, what's interesting about this is no matter what goes on inside, I can already foretell that unless the answer is 0, I can already foretell that the final result will be negative. Whatever I take the absolute value of is going to turn positive, and then we flip its sign, it'll turn negative. So that's something that you're like, all right, let's not lose that. Don't lose what's on the outside. Negative 5 times negative 7 is positive 35. The absolute value of positive 35 is positive 35. We got to take the opposite of 35, and we get negative 35. You dig? Does it make sense? Number 8. Absolute value of negative 0.8 times 10. No one said I had to use decimals in this. Well, just shift the decimal over. Negative 0.8 times 10 is negative 8. But the absolute value of negative 8 is the ocho itself. 8, 8, loving it. Number 9, and by the way, all of these ones that they're showing here, we could also split up. Let me just show you this as well. This means very little to us right now. But this is also the absolute value of negative 0.8 times the absolute value of 10. We can split it up into their own separate absolute values in that way, which means it is still 0.8 times 10. We should still get that answer regardless of whether we split it up into 2 absolute values as a product or 2 absolute values as a quotient, which is what I wanted to bring up here on number 9. Number 9, we have absolute value of 27 over negative 3. So we can either divide within here and then take the absolute value, or we can split them apart, take their absolute values and then divide. If I divide within, I get negative 9. Absolute value of that is 9. Or we could have split this up into absolute value of 27 over absolute value of negative 3. You might ask why we'd want to do this. I'm trying to think why I specifically would want to for a problem like this. But the fact of the matter is you can. And 27 divided by 3 would still give you 9. So there's no change in result. I can think of other equation types, specifically with graphing and things like that, where I'd want to do something of that accord. That's not necessarily relevant here. Lastly, of this set, number 10, which I won't split them up. Let's take a look at what we have. On number 10, we have the absolute value of negative 12 fourths, which looks a little weird to us, right? A lot of things I'd like to talk about with this negative I kind of already have before, but the negative can apply to the numerator, denominator, or the entire fraction. The 12 is already negative. There's nothing wrong with us just saying, turn that into a positive 12 now. That didn't have to do with absolute values, by the way. That's the opposite of negative. 12 over 4 is 3, and absolute value of 3 is 3. So all good there. Yeah, do these numbers turn positive? Sure. If there's a negative on the outside, does it change negative? Sure. But the idea is until you evaluate what's inside there, we don't care what it is that we're taking the absolute value of. We don't care about what x is as a variable or whatever it is. We first have to make sure that that part's isolated and we treat the 2 separate conditions on their own. Okay, number 11 through 24, 14 problems of solve the equation, graph the solution, or solutions if possible. Number 11 says absolute value of w equals 6. So what can I take the absolute value of to get 6? Either 6 or negative 6. And listen, those are the solutions. There's nothing else I have to do to solve for w. It's already by itself, right? The absolute value of 6 equals 6. Absolute value of negative 6 equals 6. When they say graph, what they're saying is plot on a number line. I should do some sort of... I should get one prepped that's kind of ready to go. Not a big old number line, but just something along the lines of this, right? So I have this one ready to go. I'll have a 6 and negative 6. And these are the solutions that represent w and how far away they are from that halfway point, which is 0. 0 is halfway between those two, which you can see that it's 0 minus 6. And over here we have 0 plus 6, which is showing that that's the distance from 0 that we're talking about, right? Okay. Number 12. Oh, I didn't move this thing down. I apologize. That was number 11. Number 12, we have absolute value of r equals negative 2. Well, keep in mind, I can't take the absolute value of a number and get a negative. This is a case of no solution. This is also not graphable because of that. So we're going to leave it as that. You don't say r is positive or negative 2. No, absolute value of 2 is not negative 2. Absolute value of negative 2 is not negative 2. So there's no solution in a case like that. If the absolute value is by itself, if it's by itself, and there's a negative on that side for equations, no bueno. Number 13, more of the same. Absolute value of y equals negative 18. Once again, this is a no solution case. We can't take the absolute value of a variable or of a number and get a negative as a result. So we'll leave it. Number 14, absolute value of x equals 13. Okay, we can get these ones. What could x be here? What could I substitute into there and get 13? Well, either 13 could go in there or negative 13. And there you have it. Those are the two. 13 and negative 13 are both the same distance away from 0. So this is just like the previous problem. Hold on, I'm trying to paste what I copied before. Maybe it didn't copy, so I'm just going to go ahead and bring it back. That's an easy draw. Here's 0, and 13 and negative 13 are both 13 units away from 0, which seems to make sense and fall in line with what it is we're talking about. These are our two solutions for x. Number 15. Now we're starting to do a little bit different here. M plus 3, absolute value of m plus 3, equals 7. The absolute value is by itself, so what can I take the absolute value of and get 7? I'm not asking what m is. I'm asking what I can take the absolute value of and get 7. Those numbers are 7 and negative 7. So what can m plus 3 be? M plus 3 can be 7, or m plus 3 can be negative 7. It's at that stage that we go to solve for m. So I'm going to subtract 3 from both sides here. 7 minus 3 is 4, which is m. Or I can subtract 3 from both sides here. Negative 7 minus 3, it's not negative 4, but negative 10. Now, I'm not going to substitute to double check. Go ahead and do that, but we will be graphing to represent this solution in some sort of way. 4 and negative 10 are both opposite ends of being halfway between a specific number. They're both 7 away from this middle number here. If we add well, let's see. I'm not sure which way they talk about it. Hold on. Let me go back to the example thing in the book. Did they bring up on the number line that they added 7 to that side or subtracted? They said, oh, they just said 0.5 away, 0.5 away. Okay, so they didn't say either or. So for this one here, we have, I'm just going to say 7 and 7 away from this middle number. This middle number here is negative 3. That makes a whole lot of sense because this 3 that was inside of here, when subtracted over, this becomes negative 3 plus 7, negative 3 minus 7. That's where it comes from. Number 16. We have q minus 8. Absolute value of q minus 8 equals 14. So q minus 8 can either equal positive or negative 14. This part's by itself. We go ahead and set those two conditions and we solve those two equations. No extraneous solutions in these cases, by the way. I'm going to add 8 to both sides in both scenarios like this. But 14 plus 8 and negative 14 plus 8 are two different things. By the way, like I stated on the last one, you don't really want to think of it as 14 plus 8. You really want to think of it as 8 plus 14. Because 8 is your middle number. It's your middle ground here. 8 plus 14 is this number. 8 minus 14 is this other number. And I know that it's written this way, but you might want to think about it the other way, right? So 8 minus 14 is negative 6. So why do I keep saying you might want to think about it that other way? Because when they say graph it, here's 22, here's negative 6, and what's the number in the middle is 14 away from either of these. We add 14 to go this way from 8. We subtract 14 this way from 8. Boom, 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 boom. But that number in the middle is indeed 8. That's why I keep saying treat 8 like that midpoint value. That's what we're talking about there. Now, number 17 says absolute value of negative 3d equals 15. Technically, there are a couple things we could do with this if we wanted to, but we could also leave it like this as well. This is by itself as an absolute value. It's okay that the inside's negative here. Fact of the matter is d could be negative to plug in, or it could be positive because we're going to take its absolute value and this side is positive. All is good. So either this negative 3d equals 15, or negative 3d equals negative 15. And when you divide both sides by negative 3, different things arise here. D can either equal negative 5 or D can equal positive 5. Now, negative and positive 5 are both 5 units away from 0. So we're going back to the whole idea of 0. You see, as long as nothing's added or subtracted inside of here, D kind of acts as its own animal. It might be affected by the negative 3 such and such, but 0 is the middle guy where we are, I don't want to say adding and subtracting 5. I mean, you are adding or subtracting 5 from 0, but that, that's half the distance, but it's affected for a different reason. It's 3 times less than 15 there. So, this really what you can do with this problem is what I wanted to bring up is we could separate this into negative, here, I'll do it over here. You could separate this into negative 3 times D as their own separate absolute values. And the absolute value of negative 3 is positive 3. So you get 3 times absolute value of D equals 15. Now, pretty soon we're going to get in some other problems right here where we get to the stage where I could divide both sides by 3. Where we have to get the absolute value by self. So if I divide both sides by 3, I get absolute value of D equals 5. This is where we get to that scenario where D either equals negative or positive 5, and that's how far they are away from 0. So that's where it kind of makes more sense. Like, why wasn't it 15? Because we got to divide by that 3, which was not relevant to what D was going to be. I mean, it is as a whole when you divide, but it's not relevant in the grand scheme of how far away they are from 0, their middle number. Number 18 says absolute value of t over 2 equals 6. See, we can do the same thing on a problem like this where I'd probably rather do the split up to begin with so I can start to recognize how far t is going to be away from our specific numbers here. So if I split this up into the absolute value of the quotient of 2 absolute values, the absolute value of 2 is 2. So you get the absolute value of t over 2 equals 6, and get this by itself by multiplying both sides by 2. Now you get the equation that states the absolute value of t equals 12. This is the case where we're really looking into what the absolute value of t can be, or the quantity that represents that of t. T can either equal positive 12 or negative 12. And these are the distances from the middle number 0 that we're talking about here. So those are the two answers. You can get that either way, but the graph will make much more sense when you have it split up like that. So 0 is the middle number, 12 away from 12 and negative 12. And there we have it. By the way, I don't know if I've been plotting these points. Did I even graph the last one? I didn't really. I just kind of drew numbers. This one I didn't really do it either. I apologize. I've just been kind of putting the numbers. I realized I haven't been changing colors. Hey guys, hold me accountable here, will you? Remember, these are the variables for, this is M, this is M, this is how far away they are from there. It's not like a real number line, but it sort of is. All right, numbers 19 and 20. More to say. Number 19, we have absolute value of 4b minus 5 equals 19. This is by itself. I don't think that getting that 4 pulled out of here would be good because the negative 5 there. We'll leave it as is. It's just you have to look into what the solutions are and what the middle value is. It's going to take a little bit more work. Anyway, 4b minus 5, the inner quantity can either equal positive or negative 19. That's our scenario that we're looking at for these. We will add 5 to both sides to begin with, and we get 4b equals 24. Then divide both sides by 4, and we get b equals 6. Same exact action's going to happen here, add 5 and divide by 4, but it's a different number that we're adding 5 to, negative 19, plus 5 is negative 14. And 4b equals negative 14, Negative 14 divided by 4 is not a clean number. That would be negative 7 over 2 as a fraction, which is also negative 3.5. If you're more comfortable with negative 3.5, I get it. At least it's an exact answer. I'll work with it. So if we graph that, how far away are 6 and negative 3.5 from each other? That's a little bit more difficult to talk about. I mean, we're going to have to practice this part anyway when we get to these solutions. We have to find the midpoint of these two, which you can do in one of two different ways. Half the distance between the two, so find the distance between them, take half of it, and then go from there. Or the average of these two numbers. I think averaging might be a little bit faster to do. Averaging two numbers, take their mean, is add them up, divide by 2. 6 plus negative 3.5 is 6 minus 3.5. And that's 2.5 over 2, which is 1.25. 1.25 is the middle value. But the real question becomes, and I don't know if this is going to be obvious because it's not fully to people, how far away was that from these two, right? Half the distance. How far away is by the way, these are the answers for B. How far away is 1.25 from either of these? If you do 6 minus 1.25, you get 4.75. And this one's also 4.75 that way. So that's how far away they are from each other. How can you get 4.75 given the numbers that you have on screen right now? If you do 19 divided by 4, you will get that number 4.75. So that's how far away they are from 1.25. Where does 1.25 come from? 5 divided by 4. Now this is all interesting, tricky stuff. It's really hard to talk about how this thing comes to be. The 5 number comes from, right here. You saw where that 5 came from. Because remember, this is 5 plus 19 divided by 4 and 5 minus 19 divided by 4. So as a whole, what we're looking at is 5 plus 19 over 4, 5 minus 19 over 4. Those are the true solutions for B. B equals this, B equals that. That's why I keep saying start from 5, add or subtract 19, and then divide by 4 afterward. 5 over 4 is 1.25. 19 over 4 is 4.75. We're adding and subtracting those amounts. So it gets a little tricky. It's really hard to talk about on those graphs, but you can get them if you understand the process, what's going on. We'll see if I can talk about those for another problem when it comes up. Number 20. We have absolute value of x minus 1 plus 5 equals 2. I don't want to set this equal to positive or negative 2 because this 5 is kind of interfering. We have to first subtract 5 from both sides, get the absolute value by itself. So absolute value of x minus 1 equals negative 3. Suddenly, this becomes one of those equations that, I can't take the absolute value of that. This becomes a no solution case. Can't take the absolute value of, you can take the absolute value of a negative, can't take the absolute value and get a negative. Can't get a negative. Number 21, you have negative 4 times the absolute value of 8 minus 5n equals 13. That might look like a positive number on that side to begin with, but as is usually the case, remember, we're not distributing inside here. Listen, absolute values wholly protect what's inside of there. You can only enter there if you take the absolute value of negative 4, say. But it's also not one you can take the, sorry, I take it back. You can't even do that because that's a negative number. It's not the absolute value of negative 4. So this is fully protected there. We don't distribute inside, but we do divide by negative 4. We do divide by negative 4 as it's multiplying by that set. So now we have the absolute value of 8 minus 5n equals, now this number is, negative 3.25. You can call it negative 13/4, whatever you want to call it. It's a negative number. The absolute value of this equals a negative number. This, once again, represents a no solution case. Can't take the absolute value of something and get a negative. I don't know how many times I got to say that. Number 22. Number 22 looks negative from the start, right? The negative 9. But what are we going to do first with this one? That negative 3 is going to divide from both sides there. As it's multiplying by the absolute value, we divide it out so we can start getting our process taken care of. There's still an absolute value here. And this now equals positive 3. Okay, so we can continue on with this problem, right? Either 1 minus 2/3 v equals positive 3, or 1 minus 2/3 v equals negative 3. We'll work with the fraction. Let's deal. We will subtract 1 from both sides to begin with. We have to get the 2/3 v, negative 2/3 v by itself. Remember, it is a negative 2/3 v. Be careful. Negative 2/3 v equals. Now remember before how I stated that like 1 plus or 3 minus. Listen, 3 minus 1 is 2, but that comes from negative 1 plus 3. Let's not forget that. That's negative 1 plus 3, and this guy here is negative 1 minus 3. Although negative 3 minus 1 is negative 4. So we're getting closer. This might get a little trickier to talk about as a whole because we're about to multiply by this reciprocal, and I'll use a different color for this. This is times negative 3/2 that we want to do here in order to reciprocate and get v by itself. We'll get v equals 2 divided by 2 is 1 times negative 3 is negative 3. So this whole thing, negative 1 plus 3, gets multiplied by negative 3/2. A little weird. The other one was a negative 1 minus 3, and that too is about to get multiplied by negative 3/2. So times negative 3 halves. So v here will equal negative 4 divided by 2, which is negative 2, times negative 3, which is positive 6. These are the two solutions for this. Okay, negative 3 and 6. So on a number line for a graph, negative 3 and 6. Now we want to keep talking about that middle value, if you will. What's halfway between negative 3 and 6? It's actually not a very clean number. In fact, remember what we said before, it's easier when you see this as division, but negative 1 times negative 3 halves is negative 1 times negative 1.5. That's 1.5. That's the middle number. 1.5 is the middle number as we add or subtract this result. 3 times negative 3 halves is negative 4.5. So we're going to subtract 4.5 that way, and you get negative 3. 4.5 that way. And then you add 4.5 to go that way. So that becomes your two numbers there. Okay, number 23. You have 3 equals, let's see, I'll change pages. 3 equals negative 2 times the absolute value of 1/4 s minus 5 plus 3. I want to get the absolute value by itself, and it's going to take 2 steps to do it, right? Just kind of just treat it like a big X. Negative 2x plus 3 equals 3. I want to solve for x, right? It's going to take 2 steps. First thing is subtract 3 from both sides. And 3 minus 3 is 0, right? But I still want to write that 0 there. And then, I hate when they have s's and 5's together. And then divide both sides by negative 2. Now, this is a 0. 0 divided by any non-zero number is still just 0. If you don't mind, I'm going to write the absolute value on this side of the equation. 1/4 s minus 5 wrapped in the absolute value equals 0. So that's still 0 there. Boom, boom. Okay, this is 0. Can I take the absolute value of a number and get 0? Yes, with 0. So the inside can either equal positive or negative 0. Just kidding. You can only get 0 is neither positive nor negative. So 1/4 s minus 5 equals 0. There's only one option for this. And it comes from adding 5 to both sides and then multiplying both sides by 4. 1/4 means times 4. 1/4 means divided by 4. So we're multiplying by 4 times 4 over 1, however you want to put it. But 5 times 4 is 20. S equals 20. There's only one option here that S can be, which is 20. Now this comes from, once again, if you're thinking about this, it's 5 plus or minus 0, which is 5. 5 plus 0 is 5. 5 minus 0 is 5. So you're going no units away from that number times 4. Remember, the whole thing gets multiplied by 4. So the number line stuff can get a little tricky. I don't know if it's more helpful or hurtful to be describing it. I think the solving parts are more important for us to really consider as a whole in what we're doing here. But it's all about distance from a very specific number. The absolute value we're taking of is distance from 0, but our variable answers are distance from a certain number, and that's what we're trying to find with the graphs. Number 24, we have 9 times the absolute value of 4p plus 2 and plus 8, and this all equals 35. Let's do some of that work to get the absolute value by itself, first by subtracting 8 from both sides. And then we'll divide both sides by 9. So when we divide both sides by 9, now we truly reveal what's on that other side as we take the absolute value of this, 4 plus 2. And this equals 3. So it's a positive number, which means we can proceed. So either 4p plus 2 can either equal 3 or negative 3. Now, let's keep in mind what I've been saying each time for number line's sake. As I subtract 2 from both sides, treat that more like, instead of 3 minus 2, treat it more like a negative 2 plus 3. 4p plus 2 is negative 2 plus 3. I want to keep writing that. Negative 2 plus 3, which is 1. And then we divide both sides by 4, where we get 1/4. You can also say 0.25. 1/4 or 0.25. But that means this divides by 4. Negative 2 divides by 4, and 3 divides by 4. What's negative 2 divided by 4? That's negative 0.5. Let's see where that number shows up later. What's 3 divided by 4? 0.75. From negative 0.5, we add 0.75. And let's take a look at this one here. If we subtract 2 from both sides, we have negative 2 minus 3. Negative 2 minus 3 From negative 2, we subtract 3. And then negative 3 minus 2 is negative 5. And then we divide both sides by 4 here. Negative 5/4 is an answer, or negative 1 1 1/4, or negative 1.25. So when we divide this by 4, that's going to be negative 2/4, which is negative 0.5, minus 3/4, which is minus 0.75. So we either take negative 0.5 and we add 0.75 to get 0.25, or we take negative 0.5 and we subtract 0.75 to get negative 1.25. That's what shows up on our graph. Obviously, the two answers, negative 1.25 is over here, 0.25 is over here, and halfway between them is negative 0.5, for which we add or subtract 0.75. This is how far away it is from both of those. Tricky. We try and do what we do with it, and hopefully it's making a semblance of sense. Okay, number 25. The minimum distance from Earth to the Sun is 91.4 million miles. The maximum distance is 94.5 million miles. Represent these two distances on a number line. So if we're on some number line, we're talking about 91.4, and that's million miles, and 94.5 million miles. The Earth can be any point between here and here. Anywhere within here is good. So these are the extreme ends of where Earth can be with respect to that. So here are minimum, maximum distances. For now, I'll just kind of plot them like that. Represent these two distances on a number line. Boom. Part B says write an absolute value equation that represents the minimum and maximum distances. What we're going to have to do is find out how far away these both are from a middle value. And then that middle value will be represented by what we do here. It's this plus this number, this minus this number, and either work backwards from that or just write the equation straight from there, right? So what's the in-between number here? Again, either take half this distance, divide it by 2, which I probably recommend, or average these numbers and take half that, take that difference. So if I do the averaging version, I can do 94.5 plus 91.4 divided by 2, which is 185.9 divided by 2, which is 92.95. 92.95. I'm going to have to do that in my calculator. But actually, that's probably right. 92.95. So that's the middle number here, 92.95. And from here, we're going to add and subtract the same amount. What is that amount? You can either do 94.5 minus 92.95 or 91.4 minus 92.95. And the absolute value of that number gives you what we're looking for. 94.5 minus 92.95 equals 0.50 minus 0.5. 1.55? Is that right? I think it's 1.55. So 1.55 is what we add and subtract from here. That's how far away it is from either of these numbers. Remember, these are millions of miles. So when it comes to an equation, it's the middle value that we add or subtract from there. Now, when we see it in that way, right, if I was talking about x equals 91.4, x equals 94.5. See where these numbers came from. Where do they come from? They came from 92.95 plus 1.55 and 92.95 minus 1.55. So when we come up with that scenario of the plus and minus versions of that number, we have to subtract 92.95 from both sides, and then we get negative 1.55, or x minus 92.95 equals positive 1.55. That means it's the absolute value of this that can equal the positive version of 1.55. So the equation can be x minus 92.95 wrapped around absolute value equal 1.55. Now, that's one version of that we can be writing there. We can also write it in millions of miles. Let's see if we have to do that. We might have to do it in millions of miles. This is in millions. I'm just going to say it like that. Of miles. Otherwise, we'd have to literally do like 92,950,000 and 1,550,000, which is kind of just whatever. So that's the way I'm representing it that way. I hope that's making a little bit of sense. There's a lot to do with that. I don't know if the end goal meets what it is we want to do with absolute values as a whole. but it works. All right, writing equations. The shoulder heights of the shortest and tallest miniature poodles are shown. Aww. Represent these two heights at a number line. So I'm not going to redraw what's there, but I am going to construct my own number line here. I got 10 inches and 15 inches. Let's do the other version of finding that half the distance between, because we're going to have to write an equation for this one as well. Last time I averaged these two numbers, and then I found the distance by subtracting from the other. This time let's find the distance, let's find half the distance between these two numbers. 2. 5 over 2 is 2.5. Now, 2.5 is how far you have to go in either direction here to get your middle value. So it's either one way or the other you can do to do that. 10 plus 2.5 is 12.5, and 15 minus 2.5 is also 12.5. So 12.5 is the middle value for which we add or subtract 2.5. If you notice, 2.5 is the number that we get from taking the absolute value of something. The difference between our number and 12.5 gets us there. So the equation is going to be, they said heights, I'm going to use h for heights. H minus 12.5, the distance between the height of either poodle and 12.5, can be up to 2.5 units in either direction. And hopefully without doing all that extra work, it makes more sense why we're plugging in what we're plugging in. 2.5 is how far we can go from the middle value as the distance from the heights of these poodles to that average, the in-between. Numbers 27 to 30, we are going to match the absolute value equation with its graph without solving the equation. These are ones where I'm not going to redraw the equations in full. I'm just going to give letters that assign each of them. So the absolute value of x plus 2 equals 4. First of all, 4 is the distance that you go in either direction from our middle number. The question is, what is our middle number? So 4 units in either direction from our middle number. Now, is our middle number 2 or negative 2? Well, I want you to think of the values you can substitute for x. We can even try this. If these are the solutions, they said without solving the equation, we could plug them in. If I plug in negative 6 into here, negative 6 plus 2 is negative 4. Absolute value of that is 4. That actually works. 2 plus 2 is 4. Absolute value of that is 4. It's actually going to be B. The answer is going to be B here. You do the opposite of what's inside there, right? The plus 2 is a part of getting your distance actually from negative 2, not from positive 2. Distance from negative 2. How far away is 2 from negative 2? It's 4 away. 2 plus 2. How far away is negative 6 from negative 2? It's 4 away. Negative 6 plus 2. Absolute value. So it's actually B on that one. Now, when we hit number 29 on the other side, I think we're going to know what to do. So let's eliminate option B, and hopefully we can carry this the rest of the way from there. Absolute value of x minus 4 equals 2 asks, we can go 2 units to the left and right of, remember opposite of this number, 4. 2 units left and right of 4 will be this one right here. 2 units that way, 2 units that way. This answer is D. You can try and substitute those numbers there, work it out. Absolute value of 6 minus 4 is absolute value of 2, which is 2. Absolute value of 2 minus 4 is absolute value of negative 2, which is 2. Down to 2 more, and this kind of almost becomes a process of elimination, but even if you're selecting the right answer, I want you to work on why this is what it is. We're going to go 4 units away from 2 in either direction. 4 units away from 2, 4 units away from 2, and boom, we hit those 2 answers. You can try and plug them in, but this one's going to be C. Absolute value of x minus 2 equals 4. That graph is C. It says match the equation with its graph. I wonder if I should be writing the answers too. I should say x equals, x equals. I think it's too little too late. But hey guys, these points are the solutions. I hope you recognize that, because that's what I was forgetting to do on my own graph sometimes. Number 30 must be A, as we're going 2 units away from negative 4 in either direction. So absolute value of x plus 4 equals 2 is A. Now, we could solve it, but hopefully over this time you're starting to recognize that when you do that, x plus 4 is 2 or negative 2, and we subtract 4, it's negative 4 plus 2 or negative 4 minus 2 that we're doing. Negative 4 plus 2, negative 4 minus 2 that gets us there. Okay. Number 31 to 34, write an absolute value equation that has the given solutions. This should be easier. Well, this should be opposite of what we just did, but it should also be easier than what we did on the word problems with these, I guess. X equals 8 and 18. When we're thinking in graph form here, we're thinking about how far away 8 and 18 are from some number. Right? Here's 8, here's 18, here are the 2 solutions. The distance from 8 to 18 is 10. Half that distance is 5. 5 away from 8 and 18 is the number 13. 13 is the value that you add and subtract 5 from to get 8 and 18. Therefore, 13 plus 5 is 18. 13 minus 5 is negative 18. If you subtract the 13 over with x, hopefully we've been recognizing this, 8 and 18 are the distance from 13 that give you 5 units away. Excuse me. I probably spoke too much and had to sneeze as a result of it. That's 5 units from there that we're getting this one. So the distance between our two numbers and 13 is 5, whether we go to the left and right direction. 13, the middle number, goes in here, opposite of that for distance. 5 is positive because it's absolute value of one way or the other. Let's see if we can kind of keep that train a-rolling. On number 32, we have negative 6 and 10 as our x values. So, negative 6 is here, 10 is here. The distance between these two numbers is 16. Half that distance is 8. I don't really know what I'm doing with those curly braces. 8 away from 10 is 2 on the left side, and 8 away from that way is 2 as well. So this equation would be absolute value of x minus 2 equals 8, as we will add or subtract 8 from 2 to get these other two numbers. Number 33, we have x equals 2 and x equals 9. Maybe this time we have to do a little bit more in the form of, of like calculating some of the things. When I say, oh, we're 16 away, I think we understand those ones, but now we have to do it a little more so. 2 and 9. 9 minus 2 is 7. That's the distance between these two numbers. But half of 7 is half the distance between those two numbers, which is 3.5. We have to go 3.5 units this way or that way to get the middle value. That middle value will be 5.5. 5.5. So we can write that one as 3.5, adding or subtracting 3.5 from 5.5, which is our distance from x. X minus 5.5, absolute value of x minus 5.5 equals 3.5. And the last one, number 34, this time let's try the average version instead of half the distance or whatever. Let's say x equals negative 10 and x equals negative 5. Negative 5 over here, negative 10 a little farther left. What's the middle value? You could also average these two numbers. What's negative 10 plus negative 5 divided by 2? That's negative 15 divided by 2, which is negative 7.5. So negative 7.5 is the middle number. How far away is negative 7.5 from either of those numbers? Well, it's 2.5 away, right? I don't even have to call these positive versus negative. They're 2.5 away, so 2.5 and 2.5. Remember, 2.5 is what's on the other side of this absolute value thing here. We add or subtract 2.5 from negative 7.5. When it's negative 7.5 on this side, it's positive 7.5 on this side. This is x plus 7.5 to get the distance between our numbers and 7.5. That's the answer. Those might sound tricky. I don't know if I'm doing them justice. I'm trying. I'm trying to make my words convey everything we need. Hopefully it's taking form a little bit. Numbers 35 to 44, they ask to solve the equation and check your solutions. This isn't to be on a number line. This is to make sure there's no extraneous solutions and things like that. So we'll give them a shot. Absolute value of 4n minus 15 equals absolute value of n. So we have variables on both sides. And what we're going to do is, if we treat the left side as the thing that we can set equal to the positive and negative version of the other side, we'll be good to go when it comes to solving. So either 4n minus 15 equals positive n, or 4n minus 15 equals negative n, supposedly, allegedly. Now I'm going to subtract n from both sides here, but in doing so I should probably also add 15 to both sides. Same step. Subtract n, I get 3n, add 15, I get 15. Divide both sides by 3, we'll get n equals 5. Cool. On this one, if I add n to both sides, same effect, only this time it's addition of, and I add 15 over here. Now this 5n equals 15. Divide both sides by 5, you'll get n equals 3. They said check both solutions. 4 times 5 is 20, minus 5 is 5. Absolute value of 5 is 5. This one checks out. This is good. I'm doing this mentally. Hope you know that. 12, 4 times 3 is 12, minus 15 is negative 3. Absolute value of negative 3 is 3, and absolute value of 3 is 3. So 3 checks out as well. Okay. Okay. Number 36. Absolute value of 2c plus 8 equals absolute value of 10c. Again, let's make 2c plus 8 equal plus or minus 10c. And solve from there. On the first one, I subtract 10c from both sides, as I can subtract 8 from both sides. Boom, 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 boom. We get negative 8c equals negative 8. If you divide both sides by negative 8, you will get c equals positive 1. We'll check that one out. Let's add 10c to both sides this time, as we subtract 8 from both sides like this. Now we get 12c equals negative 8. A little weirder when we divide by 12. This will become c equals negative 2/3, like this. Okay? So c equals 1, c equals negative 2/3. Do they both work? 1's a little easier to work with. 2 times c is 1, plus 8 is 10. 10 times 1 is 10. Absolute value of both 10 and 10 are 10. So c equals 1 is good. Negative 2/3, it's going to be tricky no matter what I say here. Even if I say negative 2, let's see. I might have to write this one out just to get you the idea. 2 times negative 2/3 is negative 4/3. Plus 8 is plus 24/3. So that's 20/3 we're taking the absolute value of. 10 times negative 2/3 is negative 20/3. So this becomes negative 20/3 equals negative 20, or absolute value of negative 20/3 equals absolute value of negative 20/3. That seems to pan out. It's general, in general cases like these ones, you're not going to have the extraneous solution set, right? Extraneous solution sets don't really occur in these situations until we hit those ones where we have two different things. So anyway, this one is going to check out as well. I don't know how much I'm going to be double checking a lot of these ones as a whole, except, I'll do it mentally. But it's not these ones I'm as concerned about with extraneous solutions. All right, number 37. Absolute value of 2b minus 9 equals absolute value of b minus 6. So this one, when we write the two things, 2b minus 9 either equals positive b minus 6 or 2b minus 9 equals negative 2b minus 6. This negative has to be for the quantity b minus 6. Remember, b minus 6 is a number and we take its negative. So this has more work to do, like distributing the negative to make it so. Now, there's a b on both sides that I shall subtract. In turn, I'll add 9 to both sides, and it adds with the negative 6. So I have 1b equals, and 9 minus 6 is 3. Over here, let's first distribute the negative into the b and the negative into this negative 6, which becomes a positive. Now we are going to add b to both sides of this equation as we add 9 to both sides here. But the difference is, in adding b, this becomes a 3b instead of a 1b, and this is positive 6 plus 9, which is 15. So we divide both sides by 3 here, and we get b equals 5. Try them out. This becomes 6 minus 9, which is negative 3. Absolute value of negative 3 is 3. 3 minus 6 is negative 3. Absolute value of negative 3 is 3. Plug in 5. We get 10 minus 9, which is 1. Absolute value of 1 is 1. 5 minus 6 is negative 1. Absolute value of negative 1 is still 1. So good. Number 38. We have 3k minus 2 in an absolute value, and then the 2 times this absolute value of k plus 2. Now, the 2 is technically not in the absolute value. If you wanted to do something by putting it inside of there, it is possible because it was a positive number outside of there. It would be no harm. Now, that being said, we are going to take 3k minus 2 and set it equal to 2 times either the k plus 2, or 3k minus 2 is going to be equal to the 2 times the opposite of k plus 2. Which, in a way, if you'd like to, personally, I like to just make the 2 negative as I do the distribution into there. And we're going to make sure to do that in a moment. There's no harm in doing that as it's just a product. All good. Either way, we're going to distribute 2 into both of these if you want to solve it. So 3k minus 2 equals 2k plus 4. If I subtract 2k from both sides and add 2 to both sides, Sorry about that. My little plus 2's got a little attached. It was like numbers in cursive. Plus 2 and plus 2. There we go. Now we'll have 1k equals 1 6. K equals 6. Over here, I still have more work with the distribution. Remember, it is a negative. That means both signs are going to change. So 3k minus 2 equals negative 2k minus 4. Now I have to add 2k to both sides to move it over. And add 2 to both sides. Well, I guess we did add 2 last time. But now it's a negative 4 that we add 2 with. This is 5k equals negative 2. Divide both sides by 5. We get k equals negative 2/5, negative 0.4, however you want to write that. Two answers there. Do they both work? 6 is 18 minus 2 is 16. Absolute value of that is 16. 6 plus 2 is 8. Absolute value of 8 is 8. 2 times 8 is 16. 6 works fine. Negative 2/5. Again, it gets a little wonky here. We have 3 times negative 2/5, which is negative 6/5. And then minus 2, which is minus 10/5. This is inside an absolute value. And then there's 2 times absolute value of negative 2/5 plus 2, which is plus 10/5. So we have that guy here. Negative 6 minus 10 is negative 16. So negative 16/5 is here in the absolute value. And this is 2 times. And then this here we have negative 2 plus 10, which is 8. So 8/5 inside there. Absolute value of negative 16/5 is 16/5. Absolute value of negative 8/5 is 8/5. And 8/5 times 2 is 16/5. So that one checks out as well. Again, I have no concerns for these questions on these both working. They are asking me to check, so I am doing it with you here. It's ones from like number 41 and such that I really have to be careful of for answers. Number 39. We have 4 times the absolute value of p minus 3 equals absolute value of 2p plus 8. Now, we've been doing the whole either this equals positive this equals negative this, but we always said when it's by itself. So we could divide both sides by 4, but I'd rather not deal with fractions if I don't have to in any form. So, you have other options here, right? 4 is also the absolute value of 4 or absolute value of negative 4. It's not going to change the results of what we have inside there. So I could turn it into absolute value of 4, which can then multiply, or negative 4, it doesn't matter, which can then multiply into this to become 4 times p minus 3, like that. And now it's inside the absolute value with it, which means this becomes a 4p minus 12. That's an option. This is an option if you want to work it out that way before we do any split. You could also, what was I going to do next? Or otherwise. You could also do this one and say this either equals plus or minus the version of what's on that side. It doesn't matter. But if I work on the left side, here I go. So maybe on the next problem, I'll do something like that. Oh, the next problem is fractions. The next problem, I'm probably going to do what I just did here. Invade an absolute value as long as the numbers outside are positive. You're allowed to do it. So 4p minus 12 either equals positive 2p plus 8 or 4p minus 12 equals negative the quantity 2p plus 8, like so. Now, all this stuff isn't necessarily, a requirement in the way that I wrote all these steps, right? Clearly, what it looks like I did was I just distributed inside of there, which was allowed only because that was a positive number. So you're going to see me do that in the next problem. There's some things you can probably get away with products as long as it's positive. Some things you can get away with products. You could have said 4 times p plus 3 or minus 3 is this and is that. You would have gotten away with it, but I'm showing the mathematical truths behind why this is allowed, really, is how I'm going to say it. So anyway, let's go ahead and solve this. I'm going to subtract 2p from both sides as I add 12 to both sides. And here we'll get 4p minus 2p is 2p, and 8 plus 12 is 20. Divide both sides by 2 as p is multiplying by 2, and you get p equals 10. Answer should be fine. Here I have to distribute the negative into both of these terms here, and you'll get 4p minus 12 equals negative 2p minus 8. Add 2p to both sides. Add 12 to both sides. This I'm sniffing a fraction potentially. We get 6p equals negative 4. And now we divide both sides by 6, and negative 4 over 6 can reduce to negative 2/3. And we'll leave it as that fraction. I'm not going to write a decimal of some 0.6 whatever version of what that would be. Sorry, sometimes my chair goes down here. Those are the two answers. Look, I'm comfortable with the answers there again. And honestly, you should be as well. You should be comfortable with the answers as long as there's absolute values of these variables protecting what's there. Let's go to number 40. We have 2 times the absolute value of 4w minus 1 equals 3 times the absolute value of 4w plus 2. Now, what I just did on the last problem is completely indicative of why. Actually, well, you know, there are other things we could do with this if you wanted to. Completely indicative as to, you know, why this thing was allowed and why they showed you properties before that said you could do that. So I could invade these by multiplying these by 2 and multiplying by these by 3. However, I'm not intimidated by what would happen if I divide by 2 here either. If I divide both sides by 2, then I can get this thing by itself, 4w minus 1. We can still do the same thing on this side. 3 divided by 2 is 3 halves, and 3 halves can distribute into here if you so like, because again, it's a positive result. So absolute value of this and then distributes. So it can distribute because it's positive. So that means absolute value of 4w minus 1 is the same as the absolute value of 4 divided by 2 is 2 times 3 is 6. 2 divided by 2 is 1 times 3 is 3. And we get that. So this is possible. Anyways, we keep working on this. 4w minus 1 either equals positive 6w plus 3 or the opposite of 6w plus 3. Which means distribution, right? This time, to get my terms positive here, my variable terms positive, I'm going to subtract 4w from both sides to get 2w. And here we'll subtract 3 from both sides to get negative 4. Divide both sides by 2, and we'll get w equals negative 2. On this one, post-distribution, we'll have negative 6w minus 3 on that side. Now it appears that I'd prefer to add 6w to this side to keep the terms positive, the variable terms I should say. So I'll add 1 to this side to move the constants over there. And I have 10w equals negative 2. If I divide both sides by 10, you have two options, the fraction or the decimal. Negative 2 divided by 10 can reduce by dividing top and bottom by 2. You'll get negative 1/5. You can also write that as negative 0.2 as an answer. Let me do that again. Or negative 0.2 as an answer, kind of your call. I like the negative 1/5 a little more, but there it is. Okay, I still feel good about those answers there. It's these next ones that you start to kind of question what might happen, because now suddenly it's outside of the absolute value. If you'll notice what happened on the other answers, and I didn't check on this one, but hey, we can talk about it. If I did plug in negative 2, I'd get negative 9 here, and I'd actually get negative 9 there. Even if one of them was positive, you still take the absolute value of it, and they both turn positive as a result, so you're squared away. What happens here is when you get certain answers, maybe a negative answer for h, you take the absolute value of it here, and boom, you can't get the negative version out from the absolute value, and that's where things become problematic. So right here, it's absolute value of 3h plus 1 equals 7h. It's here that I'm absolutely going to check for extraneous solutions. So either 3h plus 1 equals 7h, or 3h plus 1 equals negative 7h, but this time without it being in the absolute value, things can go a little rough. I subtract 3h from both sides here if I want to keep my h term positive. It's probably what I want to do to get it by itself. And then I divide both sides by 4, right? And you get h is 1/4. 1/4 is also 0.25. Cool answer, right? Right here, I'd rather personally add 7h to both sides in terms of keeping my variable term positive. That means I got to subtract 1. 0 minus 1 is negative 1. We have 10h equals negative 1. Divide, you get h is negative 1/10. Divide by 10, divide by 10. Which is negative 0.1. Now, here lies a problem, right? I can try 0.25, and listen, honestly, it'll work out. My double check for a scenario like this is, did I solve this equation right? And I did, right? I solved that one correctly, and it's going to be the right answer. When this is negative will be an issue because 7 times a negative, or positive times a negative becomes a negative. You can't take the absolute value of something and get a negative. So my substitution is not a full-on 3 times negative 0.1 plus 1. It's more so that this result will be positive, this result will be negative, this becomes extraneous. So there's only one solution here, which is 0.25. Now, does that technically occur for every problem here where we have them? No, there's a possibility that some other things can come into play, especially if this was like 7h plus 100, right? If suddenly it's a plus 100, clearly it'll change the answers. But 7 times even -1 plus 100, -10 plus 100 will still be positive. So you got to look and see at what's going on as a whole. This one was plain as day, going to give you an extraneous solution. Number 42, we have absolute value of 6a minus 5 equals 4a. Same stitch as before, absolute values by itself, so we're either setting it equal to positive or negative 4a, like so. If I subtract 4a here, I keep my a terms positive. That means add 5 over. And we'll get 2a equals 5. And when you divide both sides by 2, you get 5 halves, or 2.5. Should be no problem with that answer. We should feel fine on it. With this next set here, again, add 4a to both sides and add 5 over here. And here we're going to get 10a equals 5 and divide both sides by 10. And here we're going to get a equals 1/2. 0.5 is the other version of that. Let's check on these just to be sure. Again, this one should be fine because this is just the same thing if you plugged it in. All's good there. Let's make sure this is good. 0.5 times 6 is 3. 3 minus 5 is -2. Absolute value of -2 is 2. 4 times 0.5 is 2. So it does work out, right? It's because those were positive there that this thing keeps its positivity. It stays happy. It keeps its positivity, and we go forward. So both answers apply. 43 and 44 were these other special cases that we looked into. Not so much about extraneous solutions, but special cases to be based on what there is. This is where the other set might get more satisfied than the first set. Absolute values are by themselves. We do the same thing where we set the left side equal to the positive version of the right side and the left side equal to the negative version of the right side and solve. But on the positive set of this, it gets a little wonky because I have f's on both sides. I subtract that f from both sides and they cancel out, and you're left they become 0. And they're left with -6 equals 8, which is a no solution case. So there's no value for f I can substitute in that'll make the left side equal to the right side for the positive scenario. I don't know whether you call it extraneous or not. I think they called it like faulty or something like that. They said you reject it. I forget what it was, but just that part doesn't work. Is the final answer no solution? No. It depends on if this has a solution or not. Over here. So if this one has a solution, then we write that as the solution. The no solution part is nothing then. So we distribute the negative, and things work out a little better because if I add f to both sides, then here I get 2f. 1f plus 1f is 2f. -8 plus 6 is -2. Okay, now there's a solution to be had. My f's did not cancel out here. Divide both sides by 2, I get f equals -1. So the no solution case is not the answer, but that's the portion of just with that part there's no solution. F equals -1 is the only valid answer for this one. Now number 44 looks to get more of the same concern, the same woes. You can already see it right now. There's a 3x on both sides in different terms inside there. So it looks like the positive version of this is going to have the same issue as before. And I doubt the negative version will have that the problem. So the inside 3x minus 4 either equals positive version, which you'll see might become a problem, or 3x minus 4 equals the negative version, in which case, hey, let's talk about it. Subtract the 3x's from both sides. They're both gone. You're left with -4 equals -5, which just don't work. We're going to leave that, nip it in the bud, and say nothing to talk about there. No solution case, especially. We distribute the negative into this portion. 3x turns negative, and 5 turns positive. Now as I add 3x to both sides, it might go away on one side, but not on the other. And now adding 4 to this side is part of my goal in solving for x as a whole. 5 plus 4 is 9. And divide both sides by 6. As a reduced fraction, y'all, it's 3 halves. As a decimal, it's 1.5. You're calling which you'd like to write there. They're both exact. I'll take them. So 41 to 44 are your special case things. Again, I'm not substituting there as a double check. As long as both sides are absolute values, it's going to fit the bill for what you need. We're all good. Okay, number 45, modeling with mathematics. Starting from 300 feet away, a car drives toward you. Oh my goodness. That's a football field away. I have some time to move. It then passes by you at a speed of 48 feet per second. The distance in feet from the car, from you after t seconds is given by this equation. Now, it's important that we use absolute values here and that we're just saying the distance of the car from me. See, to us, negative doesn't apply as a distance. If the car is 50 feet away from me in front of me or behind me, it's still 50 feet away from me, right? It's that kind of thing. It says at what, or 60. Actually, here's a question. At what times is the car 60 feet from you? So we're just trying to find out 60 in either direction. In front of me or behind me, what times? Because there's a time when it was in front, there's a time when it's after. So we're going to set 60, d equal to 60, and we're going to solve for t within here. That's our goal. And that's kind of what we're saying. That's why absolute value is relevant for this case. That's why there should be more than one answer. So 300 minus 48t, the time in which the car's a certain distance from me, 60 feet, will either occur in front of me or behind me, like so. And this is where we solve for t. As a personal preference, I'd love to personally add 48t from both sides, make it positive. If I then subtract 60 from both sides like so these will go. So this will say 48t equals 240. And then I can divide both sides by 48 and solve for t. Sorry, I wrote a t there. I was saying solve for t. Divide both sides by 48, and I don't think that's it might be 5. 5? T equals 5. So 5 seconds into this car, I mean, I don't think they're saying they're playing chicken with me and they're trying to run me over. It's just that when the car's in front of me there, I now have 5 seconds to make a decision. I was like, no. Sorry, not 5 seconds. This is when the car started. It says at what times is the car 60 feet from you? It starts 300 feet away. 5 seconds later, it's now 60 feet away. I have about one and a quarter seconds to make a decision here. Anyway, I'm going to add 48t to both sides here as well, make that positive. And in turn, let's add 60 to both sides because 60 is negative over here. Add 60. And this is where it's going to be a later time because this is after the car's passed me. So 48t here equals 360. And we divide both sides by 48 in this case. Different story. I'm going to use the calculator this time. 360 divided by 48. And I'm getting 7.5. So this time is 7.5 seconds. So at what times is the car 60 feet away from me? 5 seconds into the old drive and 7.5 seconds into the old drive. Which means the car met me halfway between 5 and 7.5 seconds, right? 6.25 seconds. Making an argument. Number 46, making an argument. Your friend says that the absolute value equation, boom, has no solution because the constant on the right side of the equation is negative. Is your friend correct? Explain. Well, this is almost, there weren't error analysis questions, were there? We might run into some later, but this feels like the replacement of an error analysis question. So given the scenario here, no, your friend's not correct. It's not that it can't, I mean, you'd have to explore further, but this won't have no solution. It's not that it's not possible these couldn't have a solution. It's that you are prematurely looking at this thing and saying, just because this is negative, this -5 is not what we're looking for to indicate whether the absolute value of that's positive or negative. The -5, hold on a second, it's too small writing. The -5 is a premature value to consider whether we have solutions or not. Because the absolute value is not isolated. First, add 9 to both sides. Why do we have to add 9 to both sides? Because there's a -9 outside of this absolute value right here. So, if we do absolute value of 3x plus 8 minus 9 equals -5, and then we add 9 to both sides, suddenly, -5 plus 9, look, if it was still negative, then okay. But this turns into positive 4. So, because after adding 9, it's a positive, now that the variable now that the absolute value is isolated, and we see a positive, a non-negative on the other side, there are solutions. I'm not going to solve, but my friend is not correct. Basically, my friend is not correct, is the bottom line. There's more to do. There's more to do. It's possible they could have been, through probably dumb luck. What if it said 3x, absolute value 3x plus 8 minus 2 equals negative 5? Now you add 2 to both sides, it becomes negative 3. It's still not a solution. Your friend had the wrong reason for it, but they still would have been correct. In this case, they're not correct. Number 47, modeling with mathematics. You randomly survey students about year-round school. Ooh, interesting. The results are shown in the graph. All opposed, all in favor. More opposed than in favor. The error given in the graph means that the actual percent could be 5% more or less than the percent reported by the survey. Oh, I see the error, plus or minus 5%. Y'all see that? Okay. Excuse me. Write and solve an absolute value equation to find the least and greatest percents of students who could be in favor of year-round school. So when I see the plus or minus 5%, I think that means this could sway. Obviously, if this went 5% this way, plus 5, that means all in favor could have been as much as 37%, which means all opposed could have been as little as 63%. Or if we go, all in favor could have been a minus 5, it could have been as little as 27%, which means this could have been as much as plus 5, 73%. So you can see that sway of the plus or minus 5 in either direction here. They say write and solve an absolute value equation to find the least and greatest percents of students who could be in favor. In the, I don't know if I say least or greatest case. Let's see. In the least case, the least percent case, you have, let's see how I want to say this. Oh, it says in favor. Okay, I thought they meant of the whole thing. Okay, in favor, you have a sway of 5, plus or 5 from 32. Plus or 5% from 32. So x minus 32 would be inside here, if you remember how that works. Absolute value of that equals 5. The distance from the actual percentage we're talking about with 32 can be as much as 5 in either direction. So what's the percentages there? 32 minus 5 is 27% least and 37% most. Least in favor, most in favor. Okay, part B. A classmate claims that 1/3 of the student body is actually in favor of year-round school. Does this conflict with the survey data? Explain. 1/3 of the student body would be 1/3 of 100. 1/3 of 100 is 33.3, repeating, whatever. This is within your 37% range. It does not conflict with the survey data. So as long as the 33% is within 27% and 37%, you're good, right? That's what we're saying here. It doesn't have to be at 27 to 37. This does not conflict with the school data because 33.3% falls within the range of error between 27% and 37% in favor. Okay. Number 48. The recommended, there's error analysis. It's just farther down. The recommended weight of a soccer ball is 430 grams. The actual weight is allowed to vary by up to 20 grams. That means 20 grams in either direction of said accepted weight. Okay? Write and solve an absolute value equation to find the maximum and minimum acceptable soccer ball weights. Now, you might know what those will be because we can add and subtract 20 from our number, but that's what we have to come up with here. So our distance between our number and 430 can be all the way up to 20. So our setup is, this is part A, by the way. Our setup is, this can either be 430, can either be equal to 20 or equal to negative 20 as far as its high and low ends, the distance between, and hopefully we're starting to make more sense on absolute value. Notice how I keep saying distance between, right? Distance from our number. So add 430 to both sides. 430 plus 20 is where we get that number, right? That's how we're adding 20 grams. And add 430 here, or 430 minus 20 is where we get this other one, which is 410 grams. I have to write grams here. Grams. This is max and min. Part B, a soccer ball weighs 423 grams. Due to wear and tear, the weight of the ball decreases by 16 grams. Is the weight acceptable? Explain. Well, 423 minus 16 is 407 grams. 407 grams does not fit within the 410 to 450 grams accepted weight. It's below the minimum. They have to replace it. I don't know what they do. Consult Tom Brady. 407 grams is below the minimum accepted weight. I don't know what they do in that scenario, but there it is. Of 410 grams. Grams. Okay, numbers 49 and 50, we have our highly touted error analysis. Are you ready? Number 49, let's see what errors are to be had here. Describe and correct the error. Well, I hope you all see it from the very beginning. From the very beginning, we have absolute value of 2x minus 1 equals -9. We shouldn't possibly have any solutions here. They proceeded to solve. Now listen, everything they do thereafter is correct math, right? But the initial setup of setting this up as two different equations, you can't take the absolute value of something and get a negative. They set up, they solved the unsolvable. You can't take the absolute value of a negative and get a positive. Sorry, absolute value, value something and get a negative. This should be no solution. So we're going to write it like that. We're going to bold it. That's me correcting the error. Literally from the get-go, we wipe that out. Now, do people do this? Yes. Are there times where this can work? Not for equations, but inequalities, there's a possibility, and we have to speak more on that next chapter. Not for equations. Number 50. Absolute value of 5x plus 8 equals x. Let's go through their math and see what they do. They set it equal to positive or negative x. So far, so good. They subtracted x from both sides. I don't know if you can tell, but 5x minus x is 4x. They subtracted 8 from both sides. That all looks good. Added x to both sides, subtracted 8 from both sides. All is good. Divide by 4. Divide by 4. Divide by 6. That's -4/3. Good fraction reduction. We got -2, -4/3. All correct math. Their math is correct. The problem, as we've seen in these scenarios, are there's a possibility of extraneous solutions. In fact, because both of these answers are negative and x is the only thing that goes on that side, we're taking the absolute value of something and getting a negative on both these scenarios. All of the math is good, but both solutions are extraneous. All of the math is correct. However, they are not finished because they haven't tested either solution. As is such, neither solution, or both solutions appear extraneous. Right? No matter what I plug in, I can't get those negatives out. Therefore, this set has no solution. I love it. We have two different no solution cases for error analysis, and that's our first time seeing two extraneous solutions. Neither work. Neither work. Number 51, analyzing equations. Without solving completely, place each equation into one of the three categories. Okay, I'm going to copy and paste this table. And then I have to kind of copy and paste each set. Not really, but I want to drag things around. So I'm going to play with this a little bit. All right, hold please. Let me just resize this and take care of it. Hold on. Okay, I spent way more time setting this up than I should have because I resized all these and stuff. But okay, I got it all taken care of. Okay, so it says without solving completely, place each equation in one of three categories. So no solution, one solution, or two solutions. Now, two solutions. Oh, there might be more work to be had on these as well, so we might have to do these kind of in our head. Okay, all these have some extra stuff on the side. Shoot, maybe I should have. I spent way too much time setting this up. All right, so this first one, x minus 2, absolute value of x minus 2, plus 6 equals 0. Once you subtract that 6 over to this side, you'll see it turns negative. Absolute value of x minus 2 equals negative. This is a no solution kind of case. So this is one I want to drag into here. Yeah, so you have to change its size anyway. So there's one of them like that. Next one, absolute value of x plus 8 plus 2 equals 7. Even after subtracting this 2 over, getting this by itself. Notice they say without solving completely. They didn't say you can't do any part about it. You get 5 there, a positive number. That can lead to 2 solutions as long as you get a positive from that setup. So positive, 2 solutions. Next one, we have absolute value of x minus 6 minus 5 equals negative 9. Even by adding that 5 over, this is like the your friend argument case. Even by adding that over, it stays negative. So you might have struck dumb luck in stating that, hey, there'd be no solution, but it wasn't until you realize that it stays negative that you can actually make that claim. It's not because that's a negative 9, it's because after subtracting this number over, it still stays negative. So I'm just dragging that in. See, I should just write it in. Anyway, this resizing is no good, no good. Anyway, next one. Absolute value of x plus 3 minus 1 equals 0. If I add 1 to both sides, I get absolute value of x plus 3 is 1. 1's a positive number. That can get us 2 solutions. It will get us 2 solutions. It's not a can. It will. Now, these next two, listen, there's not much I can fit, and it'd be nice if we got 1 solution cases. Let's see how these two work here. These two, I'm just going to write inside here. I got a minus 4 here, and that will equal 0. That's a 1 solution case, right? So that can go in right there. 1 solution. Remember, when it equals 0, there's no plus or minus 0. There's just 0. And same thing here. When I add 8 to both sides, that's absolute value of x plus 5 equals 0. And that's also a 1 solution case there. So we have that final one that we can also get 1 solution from. So that's what we're doing with that one. I spent way too long trying to get that arranged, but we're all good to go. Those are the answers on 51. 10 more questions. Number 52, using structure. Fill in the equation x minus blank equals blank with A, B, C, or D so that the equation is graphed correctly. Oh, okay, so B is the midpoint. Let's copy and paste the graph looking thing. B is the midpoint value that goes inside the absolute value bit. D is the distance from that B value that we're trying to find with our 2 x values of A and C. So as far as this goes, this would be like absolute value of x minus B equals D. Now the final solutions are x equals A or x equals C, like that. But the answer to this guy right here for this portion looks like that. Absolute value of x minus B equals D. Okay, number 53. Oh, 53 to 56. We have always, sometimes, or never cases. Always, sometimes, or never. Complete the statement with always, sometimes, or never. Explain your reasoning. Oh, man. I wanted to get away with not having to explain my reasoning. All right, in always, sometimes, or never cases. Now, I'm not going to rewrite the sentence. But in always, sometimes, or never cases, what I wanted to state, and I state this in other videos as well, if you ever find them, because there aren't too many of them. A lot of people want to gravitate towards sometimes. You know, it's kind of like the if you don't know, guess C kind of thing. Like, oh, maybe. The thing with sometimes for me is sometimes is the one that you don't want to state unless you know for sure a case when it does work and when it doesn't work. Like, it always works with the exception of this case. That works enough for sometimes. Sometimes is it's not always and it's not never. You got to show the not always or not never. You got to show the exception to the rule. Otherwise, if you can't think of a time that it's not never, then that it's not a no, then say always. If you can't think of a time that it does work, say never, things like that. So, okay, number 53 says if x squared equals a squared, then absolute value of x is blank equal to absolute value of a. Is it always equal, sometimes, or never? Squaring numbers turns numbers positive for real numbers. Squaring numbers turns numbers positive. Taking the absolute value of numbers turns numbers positive. I believe that absolute value of x is always equal to absolute value of a. Again, squaring numbers like absolute values turns them positive. Real numbers. Squaring real numbers like taking absolute values of them always turn them positive. So that'll always be the case, no matter whether they were negative or positive to begin with. Number 54. If A and B are real numbers, then A minus absolute value of A minus B is blank equal to absolute value of B minus A. This is also an always case. They are opposites of each other sign-wise. Okay, they're opposites of each other sign-wise, but then you take the absolute value and they turn positive. A minus B and B minus A are opposites of each other sign-wise, which means taking their absolute value will set them equal, because it'll turn them both positive. It'll turn them each positive. And again, that doesn't make the definition of absolute value turning something positive, but that positivity, that positive aspect is not a part of what we're doing, though, right? Number 55, for any real number p, the equation x minus 4 equals p will blank have two solutions. Well, no, sometimes. It will have two solutions when it's positive. It'll have one solution when it's 0, and it'll have no solutions when it's negative. We literally just ran across this. I mean, this has been our whole setup. So this is a sometimes case. In this sometimes case, this is because depends on p's sign. If p is positive, greater than 0. If p is greater than 0, you'll have two solutions. Yay. If p is equal to 0, you have one solution. And if p is less than 0, one solution. If p is less than 0, you'll have 0 solutions. No solution. Number 56, for any real number p, the equation x minus p equals 4 will blank have two solutions. Yeah, it doesn't matter what p is in this case. As long as that other side's positive, you'll always have solutions. P can be positive, negative, it can be 0. It's always going to be that inside equals positive 4 or the inside equals negative 4, and you solve for x. 4 is just a constant. X is solvable. That's an always case. It's hard for me to explain what I want to state with that, but just the idea is that when you do this, you'll always have, like, I'm going to explain this through math. X minus 4 will either equal p, x minus p will either equal 4 or x minus p equals negative 4. No matter what p is, you add it over to this side, p plus 4 and p minus 4, right? X equals p plus 4 or x equals p minus 4. Whatever it is, plug it in. It's going to work. You just get those two answers. So that's how I'm going to work that one out. Number 57 is a question on writing. Explain why absolute value equations can have no solution, one solution, or two solutions. Give an example of each case. The idea is that for positive, the two solutions case, well, they say no solutions first, but I don't think it matters. For two solutions, taking the absolute value of any number will result, of any non-zero number will result in, the result, when the result of an absolute value is positive, that is because there are two numbers whose distance from 0 are equal. The positive and negative counterpart of that number. So, for example, I mean, we've done so many of them, I don't really know what to say. So let's just make it kind of tight. Let's say the absolute value of x minus 4 equals 3, like that. We either say x, oh, whatever. So like that's an example. It either equals 3 or negative 3. That's inside there, right? Let's go to one solution. One solution. Zero has no sign. And 0 is 0 units away from 0 distance-wise. So there is only one value that you can take. You can get take the absolute value of to get 0. and that is 0. It sounds really weird, but that's the one solution case. So when you say, for example, I do absolute value of x minus 4 again, and it equals 0. Absolute value of what gives me 0? Just 0. There's no positive and negative 0, anything like that. There's only one solution. Now, that's a solution. It is, but that's the only one. Now, 0 solutions, no solution. What do they say? No solution. No solution. You can't, and I've said this time and again, you can't take the absolute value of any number and get a negative as a result. And this is what no solution case looks like. No solution cases look like. So this one, absolute value of x minus 4 equals, how about negative 3? Can't take the absolute value of something and get a negative, so it's just not going to work out. Now, if this was negative out here, that's a different story. We don't have this thing by itself yet. All of these things are under the guise of having the absolute value by itself on its own side of the equation. All right, a few more questions. Number 58, thought-provoking. Describe a real life situation that can be modeled by an absolute value equation with the solutions x equals 62 and x equals 72. When we're doing, first of all, so x equals 62, x equals 72. When we think about that, they're both 5 units away from each other. So this would be x equals 67 minus 5 and x equals 67 plus 5, right? Therefore, x minus, right? I'm going full bore into, that's the mid value between, is that half the distance between. X minus 67 is negative 5, or x minus 67 equals positive 5. Therefore, absolute value of x minus 67 equals 5. Now, here's the equation. That's not the scenario. The scenario would be 5 units plus or minus away from 67. How about the temperature? The temperature. The temperature outside today will sway between 5 units between 67. The outside temperature will be plus or minus 5 degrees. Hold on, I have a symbol for plus or minus somewhere. Let me find it. There it is. Plus or minus 5 degrees. I'll say Fahrenheit. I'm going to be so particular. 5 degrees Fahrenheit from the expected temperature outside of 67 degrees Fahrenheit. There you go. There you go. Okay. And that's the equation that we use to model it. Okay, number 59. Critical thinking. Solve the equation shown. Explain how you found your solution or solutions. All right, so number 59. We have 8 times the absolute value of x plus 2 minus 6 equals 5 times the absolute value of x plus 2 plus 3. Excuse me. Okay, so in this scenario here, I mean, this one gets a little tricky, but here's the thing. Absolute value of x plus 2 is the same thing in both of them. It's almost like this was just a single x, right? Let's let this just be a big fat x for now. What would I do with a big fat x if this problem said 8x minus 6 equals 5x plus 3? You would get the x's by themselves. You'd subtract 5x from both sides. You'd add 6 to both sides here. And then you end up getting 3x equals 9. And you keep solving. Now in this scenario, that thing was just a big x, right? Now let's replace that big x with absolute value of x plus 2. I mean, this is what we're doing. We're treating it as a single quantity. We're treating it as a single, listen, there's more I got to do with it, but I subtracted 5 times absolute value of x plus 2 from both sides. It still works the same way as you do the combining like terms bit. So when that was a big x, it's not anymore. Now it's that, and I still add 6 to both sides, and I still get what I'm doing there. So we have this, and now we can solve as we did. So divide both sides by 3. We get absolute value of x plus 2 equals 3. And then x plus 2 either equals 3 or negative 3. So that's a way we can work out that problem as a for show. Subtract 2 from both sides. Negative 2 plus 3 is 1. Subtract 2 from both sides. Negative 2 minus 3 is negative 5. Notice how I'm stating that again specifically for absolute value's sake. So x equals 1, x equals -5. We're interpreting this as a single quantity to solve for it, right? That's how we're going about that one. Okay, number 60. How do you see it? The circle graph shows the results of a survey of registered voters the day of an election. Democrat, Republican, Libertarian, Green, and other. Which party's candidate will get your vote? Da, da, da. Error is plus or minus 2%. The error in the graph means the actual percent could be plus 2% more, 2% more, 2% less than the percent reported by the survey. What are the minimum and maximum percentages of voters who could vote Republican and Green? So Republican can do plus or minus 2% from 42%. So Republican has a min of 42 minus 2, which is 40%, and a max of 42 plus 2, which is 44%. Green, let's do this on the right side. This is part A, by the way. Green has a minimum of 0%, plus or minus 2%, so 0% minimum, and a maximum of 4%, 2 plus 2, 4%. Part B, how can you use absolute value equations to represent your answers in part A? You'll have the 42 for Republican be that middle value and the 2 be on either sides of it. So for the Republican one, we're going to do absolute value of x minus 42 equals 2. And for the Green Party, we'll have absolute value of x minus that inside 2. The difference between that has to be 2 as well. 2 units away, back and forth. Part C, one candidate receives 44% of the vote. Which party does the candidate belong to? Explain. Must be the Republican Party. It's the only one that's 2% away. Democratic Party could be 45% at minimum. These ones don't touch near 44%. The 44% looks like it hits the Republican max. That's the only one that it can be. Republican. It's within the, Republican. It's within 2% of 42%. It's within that range. Not 2% of, within plus or minus 2% of 42%. 2% of 42% is a completely different number. So that's that one. And the last question we have, number 61, abstract reasoning. How many solutions does the equation a times the absolute value of x plus b equal d have when a is greater than 0 and c equals d, when a is less than 0 and c is greater than d? Explain your reasoning. So a times the absolute value of x plus b plus c equals d. What I want to do before I do anything on the a is greater than 0, all that stuff, is let's get this by itself, the x plus b portion. I'm going to subtract c from both sides like this. Remember, d and c don't combine, they're just separate. These are literal equations. And then I'm going to divide both sides by a. And then I have this equation here, absolute value of x plus b equals d minus c over a. Now, let's consider the two scenarios. How about when a is greater than 0, that's a positive number, and c equals d? If c equals d, the top will become 0. It would be absolute value of x plus b equals 0 over, doesn't matter if a is positive or negative, it would equal 0. This would have one solution. It says explain. I'm showing you exactly from based on that. D minus c equals 0. Okay, next one is when a is less than 0 as a negative number and c is greater than d. That's a greater than sign. We're going to do inequalities next chapter, by the way, and when it comes to solving them. But when c is greater than d. If c is greater than d, d minus c will be a negative number. So absolute value of x plus b will give you a negative number divided by a also being a negative number, which means absolute value of x plus b is a positive number, which means we'll have two solutions. Two solutions. Because you can take absolute value of a number, get a positive, you're all good to go. Now, you could try numbers and see how it works, but it should always work in that case. All right, guys, and that'll do it for this one. This is Mr. Robinson. Thank you so much for watching. We still have one more section to go in the chapter. I do forget its name, but we'll get there when we get there, guys. Take care. Thank you. I will see you in that next one.